Okay. So, just got back. That for the most part went pretty well. So you are still trying to, this whole concept of net ionic equations. Net ionic equations, it actually makes your life simpler because the only thing you show is what's actually involved in the reaction. You don't have to write down everything else. So for, if you look at what happened in all these reactions, there were nitrates involved. The nitrates never did anything, okay? The nitrates are just there to make the solution soluble in water, okay? So it was a reaction between copper and zinc or, something like that. So as you go through this, eliminate just the things that you don't have to worry about. So for example, in these cells that we're going to look at in the back, they're all nitrate solutions, but I don't care about the nitrates because they're not involved. Now, you will run into situations where nitrates can be reduced or oxidized itself, but you would have to specifically be told, oh, hey, the nitrate is going to go through a reduction, or the nitrate is going to go through an oxidation part. So you would have to specifically be told that. If you're not specifically told something is happening with the nitrates especially, don't worry about it, okay? They're just there, they're just chilling out. Okay, so let's talk about this reduction table, okay? Because this is going to form the basis of what we're going to do today with the electrolytic cells. So it's actually going to work out a little bit better to have the quiz tomorrow, okay? So I was going to have it today, but it just isn't going to work out. So it's just going to work out better if I have it tomorrow. So yes, you're going to have an assignment tonight over electrolytic cells, but the quiz over redox is going to be tomorrow. And yes, there is going to be some stoic on it, okay? Just like on that lab that I just gave back, it's going to be a similar type problem where you're going to have like a solution, okay, and you're going to have to figure out the mass that's produced. There's going to be a big reaction where you have to balance it in an acidic solution where you do the half reactions of, your reduction, your oxidation, balance with the waters, make it work out with the hydronium ions. Okay, now, here's the deal. So if you look at this chart, okay, and if you haven't figured it out, you can glean a lot of information from this chart. So, and this is going to roll into the lab, or the demo that I'm going to do in just a second. And it has to deal with spontaneous reactions. So you have, generally all chemical reactions are one of two things. You have spontaneous reactions, you have non-spontaneous reactions. And what you'll see is there's like 3 different ways that you can look at this. We're going to start with the simplest one, and this has to do with this value of E naught. So these E naught values are under what's called standard conditions. Standard conditions with solutions, okay, which are different from standard conditions with gases, okay? Standard solutions with solutions are 1 molar solution and at 25 degrees Celsius, okay, which is actually a little bit warmer than normal room temperature. Right now we're at about 21, 22 degrees Celsius. So standard conditions are technically at 25 degrees. So the whole key to that, though, is that it's going to be 1 molar solution, okay? So 1 molar solutions make it standard conditions. If you deviate from there, then you have non-standard conditions. Like, for example, if you look at like KSP calculations. So all KSP calculations are done under 1 molar concentrations. So that's where you can get into the QSP. It's like, oh, okay, QSP is under non-standard conditions, and then you can compare it to what's going to happen under standard conditions. So if you look at these E naught values, okay, and you'll see the difference between E and E naught. We're going to get into something called Gibbs free energy, which is delta G. Okay, change in Gibbs free energy. You can have delta H, which is change in enthalpy. You can have delta S, which is standard entropy. But what you will see all the time when you have anything that involves a naught after it, that's going to mean that's under standard conditions. Okay, so just kind of get used to that nomenclature. So when you see E naught, delta G naught, delta H naught, whatever it is, that naught just means it's under standard conditions. So here's what I'm going to do. I've got a piece of copper wire, okay, and I'm going to pour in some silver nitrate. So here's the $1 million question. You can use E naught values, you can play the over-under game. So what's going to happen is that I'm going to take a piece of copper and drop it into a solution of silver nitrate. So what's the first thing we have to figure out?
Which copper is?
Okay? So I've got a chunk of copper. So how am I going to write copper wire?
Cu.
Yeah, it's just going to be Cu. Okay, that's it. Copper. Now, within the solution, I got silver nitrate. What am I not going to worry about?
Nitrate.
Not going to worry about the nitrates, right? So how am I going to write the fact that there are silver ions in there? Ag plus, right? Now, there's a huge difference, and this is why it is so important that you put oxidation states with these. Because if I just put Ag, I'm going to think, oh, you're trying to mix together a chunk of copper and a chunk of silver. Probably not going to be a reaction. So this is why it is so important that you pay attention to the little things. Because there's a huge difference between reacting elemental copper with the silver ion that's floating around in a beaker versus, oh, I'm going to react it with silver and it's going to look like, I don't know, a quarter, okay, that's coated in silver. It's like, oh, okay, well, there's a big difference between this silver and the silver that's in that beaker, okay? That's why it's so important that you pay attention to what's going to happen. Now, if this is going to happen, this is a tug of war, okay? This is a tug of war. This silver is missing an electron. Now, one of two things could happen to the silver, okay? One of two things could happen to the silver. The silver could gain one electron and turn into elemental silver. That's an option, okay? This is an option. The other option is that the silver could lose another electron, turn into Ag2 plus, and an electron. Okay? Now, in your esteemed chemical careers, short though they are, but esteemed nonetheless, have you ever seen Ag2 plus?
No.
No. You know why? Doesn't exist. It's like a cool freshman. You ever see one of those? No. In theory, they might be there. If they do, it's not stable, like a unicorn. Okay? It's not going to happen. So, but that's a possibility. So when you have Ag plus, it can do one of two things. It could gain an electron and turn into elemental silver. Now, if this is what happens, Eric, is the Ag plus being reduced or oxidized? Why?
It's gaining an electron.
It's gaining an electron, right? If it does this, it's being
Oxidized.
oxidized. Now, there are always redox reactions, right? So if this happens, where is it going to get the electron?
The copper.
It's going to get it from the copper, right? Okay? So if that's the case, the copper then is going to lose an electron, so it's going to get
Oxidized.
oxidized. Okay? So the silver would be
Reduced.
reduced, the copper would be
Oxidized.
oxidized. Okay? Now, unless you're specifically told, copper is usually going to end up at Cu2 plus. That's the most common oxidation state. So, on an atomic level, if this happens, here's this piece of copper wire. And it's got all of these copper atoms, right? And they've been together for a long time. Okay? These guys are tight. Okay? They've been through the death of neutron stars. They got tossed out into space. They reformed onto this third rock from the sun. Okay? They've been blasted, mined, processed, rolled through a mill into a little piece of wire like this. These guys have been through an incredible journey together. Okay? Now, along comes this silver ion. Okay? And the question is the silver ion going to have enough pull to take an electron from the copper? That's the $1,000,000 question. Okay? So is that electron on the outskirts of that atom going to go, see ya, been around a long time, been cool, I'm going to go hang out with the silver? Or is the electron going to have some sense of, you know, responsibility and go, man, I can't leave you. We've been through so much together. You know, and that's the fundamental question. That is the fundamental question. So how can we answer it? So, who wants to play the over-under game?
Yeah, let's do it.
You know, okay, Works wants to play the over-under game. Okay? So, now you have to keep in mind you have the silver ion, right?
Right.
So if this happens, and this is why you have to play the over-under game, so, because here's the difference. Is this going to go as it is written, or is this going to get reversed?
As it's written.
As it's written. So this would go as it is written, and I'm going to have a positive 0.80. So remember, the more positive this number is, your E0 values, the more positive it is, or the less negative it is, the more likely it is to go in that direction. The more negative it is, or less positive it is, the more likely it is to get flipped. Okay? So if this goes as it is written, I got a positive E0 value. Okay, all right? So, Works, where's CU relative to the AG plus? If you're doing the over-under game.
Under it.
It's under it, right? So here's the choice that you have to make. Are we going to go into CU2 plus, or are we going to go into CU1 plus? Unless you're specifically told differently, just assume that it's going to go to CU2 plus, because that's going to be the one that's going to occur most often. Right? So, if as it is written, this is 0.80. Now, this is going to get flipped, okay? And then I'm going to have negative 0.34. So, based upon solely the over-under game, Works, solely the over-under game, is this reaction going to take place?
Yes.
Because silver is above
Copper.
copper. Okay, so on the over-under game, it should happen. Now, Mr. Hale, you fancy yourself a good mathematician, okay? So mathematically, am I going to end up with a positive E0 value?
Yes,
Yes. Why?
because 0.8 is greater than 0.34.
Yeah, because so if I reverse this, I'd have a negative 0.34 plus a positive 0.8. I'd end up with a positive E0 value. The reaction should take place. Okay. So I'm going to take the silver nitrate, pour it in here, and set up. So we're just going to let that sit there for a while and see what happens. It's starting to happen.
It's bubbling.
Yeah. Okay. All right. So we got that going. So we'll let that go. We'll see what's going to happen. And yeah, that's going to go. Okay. Because you always get nervous when you trust somebody. When you grab like a random bottle off the shelf in the chemical storeroom, and you hope that whoever mixed it up actually mixed it up right, and it's actually silver nitrate and not, gasoline or something like that. Okay. All right. So let's talk Voltaic cells.
Whoa. Yeah, let's do it.
Let's talk about this. Okay? So, if you look at what's going to define your future existence,
Oh, okay.
okay? And literally, I mean, I'm not saying this lightly, that will, more so than any other generation that's going to face this earth, your generation is going to be determined by batteries and voltaic cells and the ability to store energy in batteries. Okay? That's what's going to define your life. So imagine, if you will, that we had cell phone technology in terms of being able to to develop the wireless web and all this good stuff. But let's say that we didn't have batteries. And the only way your cell phone would work.
Will the following students please come to the front office? Michaela Taylor, Zach Intrican, Elizabeth Gentry, and Gage Woods.
Okay. So imagine that your cell phones only worked when they were plugged into the wall. Okay, that's it. It's like a blow dryer, right? The only time your blow dryer works or whatever is when it's plugged into the wall. If it's not plugged into the wall, it doesn't work. So imagine how your life would change. It's like, oh my God, right? Now, the other thing,
Hi.
huh?
Is this a bad time to grab one of your students?
No, it's okay, go ahead.
All right. I can either grab Noah and Janine together, or I can take one now and get the other in a second.
Just take them both.
Okay.
And don't feel obligated to bring them back for a pain.
Yeah, I'll make sure to like toss them something.
Okay, good.
Oh, gosh. Street.
Yeah. Okay,
The mean
So-
streets in Mesa.
the whole function of a battery is to store electrical potential energy and then discharge it over a period of time. So I think what you're gonna see for your generation, because if you look at like Volvo was already announced as of 2030, they are not going to sell any gasoline-powered cars. They're gonna stop. Like California is gonna do away with gasoline-powered cars. It's all gonna go to batteries. So that's what's going to define your existence. Like if y'all are worried about keeping your cell phone charged, eventually y'all are gonna have to worry about, wow, do I keep my car charged? Okay? Now, the disadvantage of a battery is that, you know, if you have a gasoline engine and you run out of gas, you can call Ma and Pa Kettle, hey, bring me a couple of gallons of gasoline. Oh, okay, yeah, you bring that, you dump it in there, right? If your electric car runs out of battery and you don't have enough potential energy to run it, then that creates a whole new situation. Like, okay, now you gotta call somebody at the charger to recharge that battery. So the whole purpose of batteries is that they store energy on one side and they allow that energy to flow to the other side. And in the process, it does work, okay? And in a battery with your cell phone, that work is making your screen light up, okay? Sending a text message, searching the web. In a car, that energy is going to go to do work, to turn the wheels, to run your electronics, to do any number of things, to run your heater, run your air conditioner, okay? So batteries, and then even the next thing is that if you look at like solar arrays and things like that, and wind or whatever, that's always been the knock on renewable energy. It's like, well, hey, that's great when the sun's shining, but what are you going to do at night? Okay, or it's great when the wind is blowing, but what are you going to do when the wind isn't blowing? So what they're going to develop are these large called grid-sized batteries that are capable of storing enough electricity then to offload that energy at night. Okay, and so one of the cool ideas is actually you use water as a battery. So if you have like excess electricity generated by a solar array or by wind or whatever, you use it to run a pump, and it pumps water up behind a dam. Then at night, or when the wind isn't blowing, then that water is allowed to feed back down. That water spins a turbine, you generate electricity, you generate it that way. And then actually you lose less electricity that way than you do in storing it in a battery. It's more efficient. The problem is you have to have a big damn dam. So, all right, so we're going to go to the back. And here's what we're going to have set up. When you look at voltaic cells, you have two different things. You have an anode, you have a cathode, and you have a salt bridge. Okay? So, there's different ways that you can remember this. Okay? But the oxidation occurs at the anode, and reduction occurs at the cathode. Now, some people like to remember this in terms of, let's say you're an animal lover. It's like, oh, Mr. Burkamp, I love animals. Oh, I'm happy for you, okay? If you want to remember this in terms of animals, you can think of this as an ox and a red cat, okay? So if you're an animal lover, think of it that way, red cat, and ox. If you like letters, okay, this starts with 2 consonants, that one starts with 2 vowels, okay? So I don't remember how you, I don't care, okay? I don't care how you remember it. It doesn't make any difference. But just remember this. Now, the purpose of the salt bridge is kind of like Switzerland in World War II? What was famous, what was Switzerland famous for, besides chocolate?
Being neutral.
Being neutral, right? So the purpose of the salt bridge is to maintain neutrality, okay? That's the purpose of the salt bridge. Now, what you will hear me say again and again and again and again and again, and listen to me. The electrons do not flow through the salt bridge, okay? So we're gonna go back and I'll show you a cell in just a second. But you're gonna hear me say, I'm just gonna begin to plant this seed. The electrons do not flow through the salt bridge, okay? Let me say this again. The electrons don't flow through the salt bridge. Okay, so, Bodie, stop that. Copper and copper nitrate. So in this over here, this I'm gonna have a scoop of copper, and then I'm gonna pour copper nitrate into the solution as well. Okay, like so. Then over here, I'm going to have a piece of zinc, and oddly enough, I'm going to pour zinc nitrate into here. So you want to have, typically, you have the metal, and then the solution that has that metal with the nitrate. Okay? Now, that doesn't happen all the time, because sometimes, like, you can't build the cathode or anode out of that material. So for example, if you talk about like the reduction of hydrogen gas, okay? I can't build something out of hydrogen gas, okay? So then what you typically use is a specific metal called platinum. So platinum will allow the electricity to flow, but it won't be consumed in the reaction. Okay, so I'm going to take a piece of filter paper and I'm going to soak this in potassium nitrate, and that's typically what you use for your salt bridge. So I'm just going to put that in there. And let that soak up. Okay, so let me show you how this works. So this is your voltmeter, and you've got a positive and negative terminal on the voltmeter. So what the voltmeter does is that it basically measures how high the water is behind the electrical dam. Okay? So, like here I've got a 9-volt battery. So, if I take this and hook this up, okay, and touch this to this other side, I'm getting about 6.25 volts, okay? So what that tells me is how much potential there is for these electrons to move. So the higher the voltage is, the higher these electrons are above the dam. Okay? Now, if this battery had been run down, that voltage might be like 1 or 2 volts. So if your battery, if you go, has anybody ever had a dead battery in your car? Okay, right? You lacked voltage. Basically, those electrons didn't have enough potential energy to move. So somebody comes on, they hook jumper cables up, right? And what the jumper cables are doing is they're lifting those electrons back up and they're increasing that voltage across your battery. So typically when you talk about voltage, you talk about voltage across 2 points. Okay, so what I'm going to do is I'm going to take the salt bridge. So I've got copper and copper nitrate over here. And then I'm going to have zinc and zinc nitrate over here. Okay? Then I'm going to have a salt bridge that's going to connect them. So I'm going to take this. I'm going to drape that across here. Okay? Then I'm going to hook up my voltmeter. Now, somebody tell me what that reading.
-0.9.
Okay, so that's reading -0.9. Well, if you ever hook up a voltmeter and you get a negative value, just switch your electrodes. Okay? Okay, so now I get
About 0.9.
about 0.9 again, right? Okay. So what that tells me is that there is a potential for these electrons to move. Now, remember, Mother Nature is a lazy prima donna. Mother Nature is only going to allow things to move if Mother Nature ends up at a lower energy well. So here's the deal. So I've got copper and copper nitrate. So obviously these electrons are moving. So Mother Nature is gaining something from it, and it's a spontaneous reaction. So here's the deal. Amanda, you have your table, right? So what is, now listen to me very carefully. What is the reduction potential for copper to gain 2 electrons and turn into elemental copper? What's that value?
0.34.
0.34. Okay? Now, that's a positive number. So copper most likely wants to go in this direction. So what's going to happen over here in this cell is that I'm going to have copper ions gaining electrons and turning into elemental copper. Okay? Now, on the other side I have zinc. Now, what's the, listen to me very carefully, what's the reduction potential of zinc, like the way it is written?
Negative 0.76.
Negative 0.76, right? Now, so that really doesn't want to go in that direction. What does zinc want to do?
Go to zinc ions.
Zinc wants to go into zinc ions, right? So what's going to happen is that the zinc over here, it wants to turn into electrons. So, give that a spin, okay? So here's what we've got. So we've got copper ions and a strip of copper. Over here I've got zinc. Do I care about the nitrates?
No.
Could care less, okay? And then I've got my salt bridge, okay? Now, here's the million-dollar question. Amanda just said if you have Cu2 plus 2 electrons, that's going to turn into elemental copper, which you said, what was that number? Point what?
3 volts.
0.34 volts, right? So, is this, if this goes in this direction, is this reduction or oxidation?
Reduction.
Reduction, because it's gaining in electrons, right? So this is going to be the reduction. So if this is the reduction, is this the cathode or the anode?
Cathode.
Cathode, because it's the red cap, right? So this is going to be my cathode. Go with this. Now, if this is going to happen, so the zinc is going to get reversed, and it's going to turn into Zn2 plus 2 electrons. Now, what's that value?
Negative 0.76.
But I'm going to flip it so it becomes
0.76.
positive 0.76 volts. I add these together, I get 1.10. This is a positive number. So, should this reaction take place?
Yes.
Because it's spontaneous. Now, there's 2 ways that I can do this. Option number 1, if I just took a piece of zinc and dropped it into the copper, what would happen? If I just took a piece of zinc and dropped it into the copper, the copper would be, you would begin to see copper forming, and the zinc would dissolve, right? Because the zinc would be turning into iron. So what we're doing is that we're allowing that to happen. But what's happening by having this salt bridge and this voltmeter, we're allowing it to happen, but basically we have a battery. So now, because that electricity is flowing, now I can use that electricity to do work, okay? To turn a motor, to turn on a light, do something. Now, here's the million-dollar question. The electrons are not moving through the salt bridge. We'll talk about the salt bridge in just a second, okay? So, as time goes by, listen to me very carefully. As time goes by, what's going to happen to the concentration of my copper ions?
They're going to decrease.
It's going to decrease. What's going to happen to the mass of my copper?
It's going to increase.
So over a period of time, I'm going to decrease the concentration of my copper ions, and I'm going to increase the mass of
Your copper strip.
Yes. Now, over here, what's going to happen to the concentration of my zinc ions?
It's gonna increase.
Yeah, so as this runs, I'm going to increase the concentration of my zinc ions, but what's going to happen to the mass of the zinc?
It's gonna decrease.
It's going to decrease. So I'm going to decrease the mass of the zinc. Now, here's the next question. In which direction are the electrons moving? Are they moving from the copper to the zinc, or are they moving from the zinc to the copper? Okay,
I thought you said the electrons weren't moving.
no. I said they're not moving through the salt bridge.
Oh. What?
That's not, I said they just aren't moving through the salt bridge.
What are they moving through?
They're moving through this external circuit up here through the voltmeter.
Oh, okay.
Okay?
The wires.
I just said they weren't moving
I
through the
was so
salt
confused
bridge.
for so long.
Okay? They're going to move, they're just not going to move through the salt bridge. They're going to move through this external loop
I
up here.
think the zinc's gonna move to the copper.
So here's the question. So this is the cathode, right? So this is the anode. Because of the fact that this is where oxidation is taking place, right? So are the electrons moving from the anode to the cathode, or from the cathode to the anode?
Anode to the cathode.
Beautiful. So my electrons are moving in this direction, because here's what's happening. You can think of this in terms of like a party. So the copper ions are over here going, yo, sup, party, okay? And the zinc electrons they're hearing this, right? They're getting these text messages from their copper ion buddies over here. They're going, come on, man, peer pressure, it's a big party going on, man. You're going to end up at a lower energy state. This is cool, right? And the zinc is torn, because those electrons are going, man, I've been with this nucleus a long time. Is this something I really want to give up? They say, yep, screw it, we're out of here. Okay? So the electrons go, see ya. Electrons are bobbing out, they're moving over here. So they move because there is the potential for a good party. Okay? Now, over a period of time, what's going to happen to the number of people that are sending text messages over to the zinc ions?
It's gonna decrease because there's not as many.
Yes, so eventually you're going to have fewer copper ions over here sending text messages over there.
Because they're the copper strip now, right?
Yes.
Okay.
And once they become the copper strip, they can't send text messages anymore,
Because they're at the party.
because they're already at the party.
Okay.
Now, but what's going to happen to the concentration of my zinc ions over here?
They're gonna decrease too.
No. What's
No, they're
gonna-
gonna increase.
Right?
Because the zinc's going to the party.
Yes. Now, here's the deal. The party is over here. But here's what's going to happen over a period of time. It's like a battery. Your voltage is going to drop, because what's going to happen is that you're going to have fewer and fewer copper ions over here sending text messages. And what's going to happen over here is that this is becoming more crowded. Okay? This solution is becoming more crowded with zinc ions. So it's harder for those zincs to go into that solution. Okay? So when you look at this and you get a reading of 1.10 volts, that's a theoretical value. Now, we were reading about 0.9. Okay? We were reading about 0.9 because of the fact that, number one, there's always some resistance within the wires and within the voltmeter. So this 1.10 is a theoretical value. Okay? Absolute best case scenario. Realistically, when you do these, it's always a little bit less than this, because you're always losing some energy in the resistance of the wires. Okay? So here's what's happening. You can think of this in terms of like the alphabet. The electrons go from the anode to the cathode. Okay?
Is that always?
Yes. No exceptions. No exceptions. Because you're always going from where you are going into oxidation to where you're going into reduction. Okay? That's the direction these electrons are going to flow. Now, here's the next thing. Let's focus on the salt bridge. So the salt bridge is made of potassium nitrate, KNO3, right? Soluble or insoluble?
Soluble.
Soluble. Okay? Group 1 soluble, nitrates are soluble. This thing's like the poster child for solubility. It's like Switzerland. It wants to maintain neutrality. Okay? So here's the deal. You have copper ion, or excuse me, you have potassium ions and you have nitrate ions, right? Now, over here, what's happening to the number of positive charges?
Going down.
It's decreasing, right? Because they're turning into elemental copper. So Mother Nature is going, oh, dude, I'm losing positive charges. So what can Mother Nature do to balance out a decrease in these positive charges?
They're gonna give it some K plus.
Yeah, so your potassium,
Huh.
right, is going to migrate into here to keep this thing balanced out. Now, go back to your Chem 1 days. Is potassium a cation or an anion?
Cation.
Cation. Oh, look. Where does it move to?
Cathode.
Cathode. Whoa. Now, now, what are we doing with the number of positive charges over here?
Increasing.
We're increasing the number of positive charges. Mother Nature wants to keep things in balance. So it's like, oh, y'all are becoming a little bit too positive over here, like you're like this bubbly little person. I can't stand this right now. I haven't had my coffee. We need to simmer this down a little bit. So we need to introduce some negativity to balance out the increased positivity. What's the only source of that?
NO3.
From your NO3. So your nitrates, which are your anions, move towards the anode.
Woo.
Bam! Okay? So the nitrates are going to flow here. So this is why I said the electrons do not go through the salt bridge. The salt bridge maintains neutrality.
Switzerland.
It's Switzerland. Okay? So, now, let me roll this back over here. Now, the salt bridge is important, don't get me wrong. So, if I hook this up, okay, put these in here, right? And we're like 0.9, okay? Now, but as soon as I take that salt bridge out, the reaction stops. Because what happens is that instantaneously, the solutions become so far out of balance that the reaction stops. So that's why everybody goes, wow, the reaction stops because you took out the salt bridge because the electrons are flowing through there. That isn't it, okay? But now, as soon as I put that salt bridge back in, the voltage goes back to where it was. So, but that's how quickly the system gets so far out of whack that the voltage drops to zero. Now, obviously, if I take one out, wow, it stops. So, when you look at these E0 values, okay, so again, if you have a positive E0 value, basically what's going to happen is that we're going to allow these electrons to flow. And they're only going to flow because of the fact that there's potential. Mother Nature is going to gain something from it. Mother Nature wants this to happen because Mother Nature is going to end up at a lower energy state. Got it? Good? Grand? Okay, back we go. So sometimes when you see cells written, you'll see it written as what's called standard line notation. I did, and also a little bit of terminology depending on which book you're using. So if you see something referred to as a reductant, okay, that just means that it's reducing agent, okay? So sometimes when you're reading about cells, they'll say, oh, it contains the reductant, okay? The reductant is the same as the reducing agent. But if it's the reducing agent, does it contain what is oxidized or what is reduced? What is oxidized, okay? So that's kind of the dichotomy. So your reducing agent contains what is oxidized, and your oxidant, which is the same thing as your oxidizing agent, contains what is reduced. Now, if you were to look at your reduction table, where would you find the best oxidizing agents? On the left side or on the right side? If you were to find the best oxidizing agents, would you look on this side or on the product side? Left. Top or bottom? Top. Because those are the ones that are going to be most likely to take electrons and go in this direction. If you wanted to find a horrible oxidizing agent, reducing agent, where would you look? If you wanted to find a horrible reducing agent, would you, a horrible reducing agent, right? Which means that it doesn't want to get oxidized. So if you have like silver, do you think silver wants to get oxidized? No. So if you want to find horrible things that are willing to get oxidized,
Top right.
top right. If you want to find things that really want to get oxidized, where would you look?
Bottom right.
Bottom right. Okay, because those really want to get reversed and go in that direction. So if you look at what we did, okay? If you look at what we did, and again, you can play the over-under game. So I'm going to pass this around before I forget, okay? So I'm going to pass this around, and you'll see a whole bunch of silver crystals that have formed from the single displacement reaction. So the other thing that you'll notice is that this solution now has a blue tint to it. So if you paid attention back there, what was the color of the copper solution? Blue. Notice that this is getting a blue tint to it. So what we've done is that we took elemental copper, okay? It went into the solution. We have a bunch of copper ions. We've decreased the number of silver ions, and that's what's plated out on here. So it's just kind of cool to look at. So take that, pass that around. Okay. So what we did in the standard line notation, so here's what happened. Was the zinc my anode or my cathode?
Anode,
Why?
because it was oxidized.
Okay, because the zinc gave up its electrons, right? So this is what's happening at the anode, and this is what's happening at the cathode, right? So this is just a shortcut way of drawing out these cells, okay? But here's the deal. As this is what you have to be able to understand. As this reaction goes on, what's going to happen to the concentration of my zinc ions?
It's going to increase.
It's going to increase because I'm making more and more zinc ions. What's going to happen to the concentration of my copper ions?
It's going to decrease.
It's going to decrease, okay? So right away, basically, as soon as this reaction begins to run, I'm going to see a change in these concentrations, okay? So that's why I said when you look at these E0 values, those are under standard conditions where you have 1 molar solutions. As soon as these reactions begin to start, you lose those standard conditions. The zinc ion concentration is going to go up. The other concentration is going to go down. Okay? Let me see. Got that. Got that tape.
So when you have a salt bridge, right,
Yep.
does the salt bridge need to be like one piece? Or could it be two separate pieces?
What do you mean?
Like, since
Like-
nitrates are going into one and potassium ions are going into the other, if you just had both of them, like just,
Like two
If you just had a
strips?
strip at each one,
yeah,
no, they still has to be connected across that. Because it's like both sides have to sense that what both sides are doing.
okay.
Even though the electrons aren't going through there, they still have to sense,
They have to see that drop in nitrate.
Yes.
And then, okay,
yeah. Because otherwise it's gonna get out of whack.
So,
yeah.
would eventually the salt bridge lose all of its electrons or cations and
You
anions?
have so many, yeah, if you let it go long enough, but you have such a high concentration to start with, that isn't what's gonna,
Okay.
it's gonna be what's gonna happen in the cells is what's gonna stop it first. Okay. So, I'm done. Let me make sure I got through everything. And now I remember that one last thing. So if you look at like in terms of a battery, your anode has the negative charge and your cathode has the positive charge. That's one thing I forgot to say. Here's the easiest way to remember that is that cathodes have a T in it and that looks like a plus sign. So that's how you know, that's how I always remember that the cathode is the one that has the
Or
positive charge.
cation is usually positive and anion is usually negative.
That too. Whatever works. Okay. So this is out of your book. It's a relatively short assignment.
It is. You're so sweet.
Like 20 questions.
Yeah, it's relatively short. Here's 63 questions.
No, it's not that many. This is going to take me a while to explain everything that I want done.
Yeah, but Mr. Hammond.
It's not, he's not as tactically trained. Wasn't he military?
Those three actually are very
He was in Alabama.
like,
Okay.
Very similar at least.
Yeah, relatively short.
Okay.
27, 28, 30. Is 30 the last one you wrote?
Yeah. All right. So when you get to questions 13 and 14, on these two questions, 13 and 14, just do A, B, and C on both of them. Okay? There's other parts to them. Just do A, B, and C. When you get to 26, when you get to 26, only do A and C, but I want to see, these are where you're going to balance these half reactions, okay? I want to see the reduction half reaction, I want to see the oxidation half reaction, and then I want to see everything canceled out, okay? And again, just do 26, A, and C. Don't do the whole thing. Just do 26, A, and C. And then 27, 28, 30. When you do these half reactions, make sure that you write down the charges, okay? Are the odd numbers or the even numbers in the back of the book?
Odd.
Okay, so let me give you a hint on 26.
A.
So on 26A, if that goes right, you're going to get 4 waters.
On the right side?
No, I'm not going to tell you. You're just going to get 4 waters. On 26C, you should end up with 11 waters.
Oh, God.
C, not D. I'm sorry.
It's okay, dude.
26C.
Okay.
26C is a fun one.
Fun by your standards?
No, it's not. It's not fun by any standards.
Okay, cool. Glad to know.
Are you done?
No.